Hey everyone, so this video is a chapter 10 topic on solution stoichiometry. So in the previous videos, we already covered just stoichiometry, limiting reactant, percent yields, and now we're going to move on to solution stoichiometry. Let's go to our slides. So in solution stoichiometry, you're not going to start out in grams, right? In previous problems that we did, you would start out at gram A, and then you go to gram B, right? Because they're in the solid state, right? So if you're in the solid state, you're going to see grams. But what if you're in the solution state? And this is a lot more common in the real world because solids don't react with each other very well, right? You can't just smash two solids together and get a compound. You want to take a solid and you would dissolve it first to increase the basically the surface area. It just reacts better when things are dissolved. So you want to dissolve something first into a solution, and then you react the solutions together. Okay. So what that means is we need to review molarity. You guys know that already, but remember that's how you measure the concentration. Is to figure out the moles of solute in a given amount of solution. And that is measured in liters. So therefore, molarity is this moles of solute over liter of the entire solution. It tells you how concentrated, right, how much solute is in there. So if you have more solute, you have a higher concentration than if you have a smaller amount of solute, right? And so the molarity allows you to figure out how much is there in solution so that when you're doing stoichiometry, you can figure out the ratio, right? The amount that is there to react. So as a review, you guys should probably go and practice molarity going from moles to volume and volume back to mole using molarity. Okay. Okay, so how solution stoichiometry works. Let's go to the board for this. So far, this is what we have for the roadmap for doing stoichiometry, right? So typically, if you're in the solid state, then you start at grams, right? You take a solid, you go to, the balance, and you mass it out in grams. You get grams of A, and then the stoichiometry problem asks you to, get to grams of B. So, likely you have, a solid. That would be, that'd be convenient to mass out, okay? But what if you don't have a solid? Instead, you have a solution. So now what you need is a volume to figure out, how much you need of something that's in a solution. You have to measure it out by its volume. So you have liter of solution A aqueous, right? Here A is like maybe solid or liquid, right? Or gas even, okay? But if you have something in solution, right, you'll need to measure out a liter, an amount in volume in order to get moles, okay? So you'll need the molarity of A in order to go from liters of A to mole of A. And on the B side, it's the same, right? It'll mirror it. So liter of B aqueous. How do you get to mole of B? You use the molarity of B, okay? So that's converting between volume of A and mole of A, volume of B and mole of B. You'll need molarity, okay? That's why I was saying maybe you want to go back and practice just converting between those two, just like you guys are so proficient at converting between grams and mole right now using molar mass, okay? It's a very similar calculation, right? Desired unit on top, as always, right? To get to moles, okay? So what you'll notice about the roadmap then is that all roads lead to mole. And as I mentioned in previous videos, mole is where you want to be at because that's, you want amounts of things, countable amounts of things reacting, right? So you always want to go to moles rather than staying things don't react in grams, right? It reacts in moles. So all roads will lead to mole, and you need to get to mole to cross the bridge to the other side, right? So that's what it's what you notice here, right? Everything goes to mole first. Okay. All right. So in this part of the video, the last part, in previous videos, we've concentrated on this region of the roadmap. In this video, this is the region we're going to concentrate on. So we'll be asked, to start at volume of A and end at volume of B. Okay. And so we'd have to go to mole A first, mole to mole ratio to cross over to B, right? And then molarity to get to volume. Right? Okay, so let's go back to the slides. It's going to give us some examples to practice. Okay, let's look at this one. How much of a 0.115 molar potassium iodide solution in liters is required to completely precipitate all of the PB2 plus in a 0.104 liter of 0.225 molar lead nitrate solution? Okay. So what are the two things that are being related here? Ki and PbNO32. Okay. Notice that even though it mentions lead 2 plus, right? That is not what we're trying to calculate, right? Because it's asking how much of Ki given this much lead nitrate. So therefore, the two things you're relating is Ki and PbNO32. Those are your A's and B's. Remember, you always want to, figure out what A and B are first. Okay. All right. So let's do this one on the board. Okay. So how much of a 0.115 molar Ki to react with a 0.225 molar, oh, and I think it gave us a volume too. Let's see. Yes. With 0.104 liter of 0.225 molar PbNO3. Okay. All right. So first, what we want to do, right, is figure out what state of matter we're in. So remember on your roadmap, right? You start at grams if you're, a solid or a liquid or maybe even a gas. But here, you guys see molarity, right? You see molarity, you see a volume, so therefore you know that you're in that aqueous state and you need to take the top path, right? And so make a plan here. Okay, where do you start? You start with what you're given. And remember, what you're given is two things in solution stoichiometry. You need to be given a volume and a molarity. If you're not given those two things, then you're not given anything, okay? So notice here, you have a molarity, but you don't have a volume, so you don't know anything. That's why, that's the question, right? Is the how much. So again, what you're given is always a volume and a molarity, because that's the only way you'll get to moles, okay? Those are the pieces of information that you need to get to mole. So where do you start? You start with liters of PbNO3 2. And you're gonna go to moles of PbNO3 2. Then you go moles of the other thing, moles of B, which is mole of Ki. And then it's asking for how much in liters, right? Liters of Ki. Okay. Right? So your roadmap gives you that. So now we execute. We start with the volume, 0.104 liters. And anytime you see a molarity, guys, see, remember I told you in a previous video, anytime that you see a molarity, you're going to translate it to moles over liter. So 0.225 molar is moles over liter. That allows you to set it up here as a conversion factor. You know you want moles on top, so you're going to write 0.225 moles of PbNO3 over liters. Okay, so the liter cancels. Now you go to mole-to-mole ratio of lead to nitrate to moles of Ki. So mole of Ki, that's 2 moles of Ki over 1 mole of PbNO3 2. Okay. And now you need to get to the volume. So again, remember, going between moles and volume, you'll need a molarity. But this time, you need the molarity of Ki, which is this. Again, rewriting that as 0.115 moles of Ki over liter, right? When you rewrite it like that, it's easy to plug it in here. Well, we know that we want liter on top because it's asking for how much in liters. So we have liter on top and 0.115 moles of Ki on bottom, right? We know that that has to be on bottom so it can cancel out. And now we just punch that in. So 0.47 liter of a Ki aqueous solution. Okay, so what we're saying is it'll take 0.407 liters of Ki in order to completely precipitate and react with 0.104 liters of this, right? To completely precipitate out lead to iodine. All right. Let's go back to the slides. Okay, and let's do our second example problem. How many liters of a 0.0623 molar barium hydroxide are needed to react with 0.438 liters of a 0.107 molar HCl solution? Okay, so again, let me put that on the board. Okay. All right, so again, let's look at the two things we're relating. What are the two things reacting? Barium hydroxide and HCl, right? That's our A and our B, okay? We make a plan. Where do we start? Remember what I said? You need to find the thing that has both a volume and a molarity. That's where you start. Which thing? A or B? Is it A or B that has both a volume and a molarity? It's HCl that has both a volume and a molarity. That's where you start. So you start with liters of this. So liters of HCl goes to, right? Convert to moles of HCl first, then go to mole B, or B is barium hydroxide. Okay. And then it's asking for how many liters of volume of B. So liters of barium hydroxide. Okay. All right, let's execute. Liters of HCl. How many liters? 0.438 liters. Okay. And we want to get to moles, right, of HCl. So remember, anytime you see molarity, think of it as moles per liter. So that's 0.107 moles of HCl per liter. Right? So which one's going to go on top? Moles of HCl. Because we want moles of HCl to come out, right? Liter is going to be on bottom. Right? You can just do like that. And then mole to mole ratio. Moles of HCl, that's 2 moles of HCl. To barium hydroxide, that's 1. We want barium hydroxide on top. So we put 1 mole of barium hydroxide on top and 2 moles of HCl on bottom. And then for the volume, you're going to put liters on, you want liters on top, right? And here's the molarity. So 0.0623 molar is going to be 0.0623 moles of barium hydroxide over liter. So that's going to be liter of barium hydroxide on top over 0.0623 moles of barium hydroxide bottom. Okay, and then we punch that in. It's 3 sig figs, so 0.376 liters of barium hydroxide solution. So you put aqueous, that's what you mean, right? Because everything's in solution. All right, guys. So as I always say, right, you got to go and practice this and come to office hours if you need help. All right. I'll see you guys in the next video.